This is the Cayley table of the symmetries of a tetrahedron. The tetrahedron has 24 symmetries, which means that this Cayley table is 24 by 24, 576 entries in all. This group is really quite small compared with the groups that research mathematicians study, but already it reveals one of the problems. How can you possibly understand the structure of this table? How can you possibly make sense of such a large, confusing array of symbols? Well, sometimes a hint of structure emerges almost by accident. Some of these symmetries are direct symmetries, rotations of the tetrahedron. These are indirect symmetries, which involve a reflection. And if you continue this coloring, a simpler pattern emerges. The table has an overall block structure. For example, if I combine a direct symmetry with an indirect symmetry, I get an indirect symmetry. It's just as if I had a simpler 2 by 2 structure involving compositions of direct and indirect.
Something else emerges from this blocking of the Cayley table. If you look at just the direct symmetries, you get a subgroup, a smaller group of order 12 inside the larger group. In this program, we'll be looking at subgroups, and later you'll see another subgroup of the tetrahedron group which gives a different blocking of the Cayley table. What subgroups can you have? Lagrange's theorem gives part of the answer. The order of a subgroup must divide the order of the group. So in a group of order 24, these are the only possible orders of subgroups, the numbers that divide 24. You won't find any subgroups of order 5, for example, because 5 doesn't divide into 24. You might not find subgroups of all these orders, but you won't find any subgroups of any other orders. You'll be seeing an informal proof of Lagrange's theorem later. The basic strategy is, first pick a subgroup, then compute some subsets of the group called cosets. These cosets all have the same size as the subgroup, and they partition the group in a way that makes Lagrange's theorem an obvious consequence. So just what is a coset? Ian?
To answer that question, I'm going to build a new model of a group. I'm going to start with something with less symmetry than the tetrahedron. In fact, I've chosen a triangle, and I'm going to look at the symmetries of that. I've colored the triangle like this. Colorings are going to be rather important in our study of cosets, but here I've painted the triangle just so that you can tell how it's placed. For example, if you start from here and apply the symmetry of rotating through 2 pi by 3, you get this. I'll keep track of this by putting the triangle over here and showing the symmetry by this rod. This rotation is called A, and that's one of the elements of the group. The triangles are there to help you keep track. It's the rod which is the group element. Suppose that I start from here and apply A again. I get this. To show that on my model, I need another rod labelled A here. And that's an important feature of this model. The elements of the group will each appear several times. Now, what else can I say? Well, I could have got directly from this first position to here by one symmetry, a rotation through 4 pi by 3. That's called B in our notation. In fact, because this is a group, it's always possible to go from any orientation to any other in a single step. So there's a way of getting from here to here. That turns out to be the symmetry B again. Of course, in a group, every element has an inverse. So every rod has a label in each direction, with the labels being inverses of one another. I ought really to be adding the identity symmetry at each corner as well, like this, to show that the identity takes you from any orientation back to itself. But I'm going to leave out the identity from now on to simplify the model. I've now got the three orientations that result from direct symmetries of the triangle. Of course, these symmetries by themselves form a subgroup, but there are indirect symmetries as well. Suppose that I reflect in this axis. I get a triangle that looks like this. Getting there is another symmetry, one called R. Now R is its own inverse, so this rod is labelled R in both directions. Now I can go on like this, and here's the finished model. I've not labelled everything because that would be too confusing, but you can see that from this corner, for example, these 5 symmetries take you to the other 5 corners. And of course the identity takes you from this corner to itself.
So that's Ian's model, and it gives you the same information as the Cayley table. For example, suppose you want to find a circle R. The table tells you it's T. Now let's see that on the model. Remember that a circle R means do R first, then A. And you get T just as before. The model and the table carry the same information. Now remember where we're heading. You want to prove Lagrange's theorem using cosets. The cosets will turn up in a moment, but you need to start with a subgroup.
Now this is where the colourings come in. Last time I built a model using this pattern. I deliberately chose one where you could tell which way up the triangle was. Suppose that instead I use this colouring, which has some symmetry itself. Now, when you apply rotation A, the picture doesn't change. Nor does it if you apply rotation B. Not all operations will leave it the same, however. A reflection like R would swap over the light and dark areas. So there are 2 different pictures. And here's the model of the full triangle group, except that I've coloured the triangles in this new way. And you can see that here and here and here, I've got the pattern one way round, while here, here and here, it's the other way. These 2 pictures are going to be associated with cosets, 1 picture to each coset. But before I make that clearer, I need to show you the subgroup. These symmetries, A and B, together with the identity, preserve the original picture. So they're a subgroup of the full triangle group. In fact, it's the subgroup of direct symmetries. So you've got a subgroup, let's call it N. The subgroup is one of our 2 cosets. And here's how you get to the other coset. Choose an element that isn't in N, say R. Using R takes you from the original picture to its reflection. Here, and here, and here. So there's another way of looking at this model. If I lift up one set of pictures, you get all of one set of pictures on the bottom and all of the others on the top. Here, on the bottom, is the subgroup N. These are all visually the same because N is the symmetry group of this picture. Now, what does R do to each of these? R changes the picture each time. Here, here, and here. So everything up here must be the reflected picture. Now I can show you the cosets we've talked about. One coset is the subgroup N itself. It's the set of symmetries E, A, and B that preserve the picture. The other coset is the set of symmetries that change the picture. That's R, S, and T. In the model, the subgroup symmetries occur horizontally here in the bottom layer. And the other coset is the set of vertical rods. But it's convenient and quite helpful to think of the cosets as being the two layers, the subgroup coset and the other coset. I've already labelled this coset N, and I label this one Rn to show that we obtained it using R and N. Actually, as well as Rn, this coset could equally well have been called Sn or Tn, because S and T make the same change to the picture.
So now we split the original group into two parts. One of them, the subgroup coset, and the other, the coset corresponding to this other picture. Let's see how you might express that in symbols. We started with a subgroup N. That's the elements E, A, and B. To form the other coset, we chose an element R, not an N, and combined it with each element of N in turn. The coset Rn is the set of elements you get. And that's the set R, S, T. Notice that the second coset is not a subgroup. It has no identity. It's just a subset of the symmetries. On the model, you saw that the coset could equally well be called Sn or Tn. Sn has these three elements. Tn has these. The elements in Rn are the same as those in Sn and in Tn. But now let's see how the idea of cosets works when we choose another subgroup of the triangle group.
The subgroup this time comes from considering this colouring of the triangle. Any rotation of the triangle will alter the picture you get. And in fact, there are three different pictures, one with each of the different corners coloured. But the reflection that we've called R, a reflection in this axis, will result in the same picture. And that's the only symmetry, apart from the identity, that preserves this picture. So here's our subgroup, which we're going to call H. The two-element subgroup consisting of the identity and the reflection R. Let's make the subgroup the bottom layer as before. This picture on the second layer gives a second coset. But what should I call it? Well, the symmetries that change the original picture to this one are A, here, and here, and T, here, and here. So the coset is AH or TH, as you please, the set containing symmetries A and T. And the third layer, that turns out to be BH or SH.
How does this help you prove Lagrange's theorem? The key is this. The layers, the cosets, are all the same size. Each coset is in some sense a copy of the subgroup. All the cosets have the same size, so the number of elements in any coset must divide exactly into the order of the group. But the subgroup is one of the cosets, so its order must divide the order of the group. In this case, the group has order 6. The subgroup has order 2, and 2 divides 6. Here, the subgroup has order 3, and 3 divides 6. But even though both of Ian's models fit in with Lagrange's theorem, there's an important difference between them. And that will lead us to the crucial idea of a normal subgroup. It hinges on the fact that with this model, the upper layer is an exact copy of the subgroup layer, in the sense that the symmetries here are the same as those here. whereas with the other model, that turns out not to be true. In the first model, you started with this picture, with symmetry group N. The other coset corresponds to this other picture, and its symmetry group is also N. But in the second model, you started with this picture. Its symmetry group is H. The other cosets have these pictures with these different symmetry groups. So what? Well, it turns out that this idea tells us whether or not the Cayley table blocks.
The idea behind blocking was that you treated some set of symmetries as if they were the same for some purposes. All direct ones the same, and all indirect, for instance. Suppose that you took this model and drew together the pictures that are visually the same, here and here. You'd get this model. This cluster of symmetries came from here and will take this picture back to itself. This cluster will take you from this picture back to itself. And these symmetries will move you between the pictures. Rather brutally, I've simplified the structure. Start here, say. Any of E, A, or B, followed by any other of E, A, or B, even the same one used again, is equivalent to just one of them. So, E, A, or B preserves both pictures, while R, S, or T moves between pictures. You're seeing the beginnings of a group structure, a group with two elements. The first is E, A, or B, and the other is R, S, or T.
This is Ian's new group structure. If you combine any of E, A, or B with any of E, A, or B, you end up with one of E, A, or B. Let's replace these sets with their coset names. This is N, the subgroup. And if you combine any of R, S, or T with R, S, or T, again you end up with E, A, or B. So you can put N here too. And it turns out that the other combinations just give us Rn. Everything works out, and you end up with this blocked table. Hidden in the 6 by 6 group table is the structure of a group of order 2. But do all subgroups of our group give rise to a block table? No, they don't. And you can see that by considering the other colouring of the triangle. If you tried to coalesce the layers of that model, you'd find it doesn't work. You'd get something like this. The symmetries don't divide up into nice subsets. A, for example, is paired with R, S, or T, depending on where you are. And you also get trouble with blocking. The subgroup consists of E and R, so you start like this. That does seem to block. But here it breaks down. These elements are a mixture from different cosets. And that happens in other places too, so you don't get blocking. Let's summarize. If you start with this colouring, then the symmetry group of each picture is the same, and the Cayley table blocks. We call the subgroup a normal subgroup. But if you start with the other colouring, then you get coset pictures with different symmetry groups, and the Cayley table doesn't block. There the subgroup is not normal. Normal subgroups give you blocking, so you can spot a group structure within the Cayley table, and that group is called the quotient group. So now, let's return to Ian's 24 by 24 table. You've already seen one normal subgroup, but is there another? And if so, what's the resulting quotient group?
I have to start with a subgroup. Earlier, we found subgroups by considering colourings of the triangle. So now, I'll get a subgroup by considering colouring a tetrahedron. The colouring I've selected is this one. And there are just 4 symmetries out of the 24 that keep it looking the same. One of them is this. That's called A in our table. By putting my hands in similar positions on the other edges, I get two more. This one, B, and another one, C. And of course, there's the identity. But not all symmetries preserve the picture. This rotation, called D, changes it to this. And now you can take a big leap forward because we've built the model for you. Here's the subgroup. I'm going to call it N, and it preserves this picture. As usual, I've omitted the identities, which should loop round at the corners. And I've economized on tetrahedra by putting just one in the middle. There ought to be one of these at each corner. In fact, I've missed out most of the rods as well, because they obscure the details. Now, with a 4-element subgroup, you'd expect 6 cosets, each with 4 elements, and each one corresponding to a different coset picture. Here they are. This picture's associated with this coset, this with this one. These are the layers of my model. For example, I can get to this layer using the symmetry D, which changes this coset picture to this one. The question is, how can I use this model to help to decide if this subgroup is normal? Well, the subgroup is normal if and only if each of these 6 coset pictures has the same symmetry group. How can you tell that from this model? For each layer, you need to look at these rods, the symmetries that preserve the coset picture. Only if each layer is the same group of symmetries is the subgroup normal. It turns out that these rods are the same symmetries E, A, B, and C that are in N. This coset picture does have the same symmetry group as the original picture. For example, if I apply symmetry A, the tetrahedron stays visually the same, as it would with B or C. And the same is true for each of these 6 cosets. So the subgroup is normal in the tetrahedron group. And that means that there is a blocking of this large Cayley table that exposes the hidden quotient group structure. In fact, this is it. And it's an interesting quotient group because it turns out that it's isomorphic to the triangle group. Within this large Cayley table is a smaller 6 by 6 table that we've been studying for most of this program.